This is the screencast for section 2.2, example 8. We're going to look at finding and proving that one function is a right end behavior model of another one, and also a left end behavior model. Now to do that, we have a definition here. A right end behavior model for a function occurs if and only if the limit as x approaches infinity, so off to the right, hence right end behavior model, of that function divided by the end behavior model equals 1. See, the thing is, if their y values are getting very close to being the same, then when you divide them, they should be getting very close to 1, because a number divided by the same number is 1. And then same would occur as a left end behavior model as x approaches negative infinity. So example 8 says let f of x equal x plus e to the negative x. Show that g of x equals x is a right end behavior model. And then we're also going to show that h of x, which is e to the negative x, is a left end behavior model. Alright, so to show first there is a right end behavior model, let's take the limit as x approaches infinity of our function, so x plus e to the negative x, over what we think the right end behavior model is, and see what happens to that limit. We've got limit properties that say we can separate the limit of x over x plus the limit of e to the negative x over x. Well, x over x simplifies to be 1. And then over here, e is being raised to a negative exponent, so it really drops down to the denominator, which means that denominator is going to get infinitely large. Therefore, this is going to approach 0. So my overall limit is 1. Therefore, g of x equals x is a right end behavior model for f of x. Now let's work on that left end behavior. So the limit as x approaches negative infinity of x plus e to the x, or e to the negative x, our function, over e to the negative x should equal 1. So let's give it a try. Again, we're going to use our limit properties and separate the denominator here. So now this one's going to get a little bit complicated. We're going to have to think about it numerically. E to the negative x is in the wrong spot, so this should be xe to the x, the positive x, all in the numerator. Alright, now this one simplifies to be 1, so the limit of it is just 1, no problem. On this one, back to the complicated one, x times e to the x is getting a whole bunch of negative numbers plugged into it, so that will drop down to the denominator. So regardless of what x is, e to a negative exponent that keeps getting bigger and, or well, smaller and smaller and smaller, more negative and more negative, is going to drop down to the denominator and therefore is going to approach 0. So if you think about negative a million, you have negative a million times e to the negative 1/1,000,000th. That is huge, and that's going to drop down to the denominator. So our values, the denominator is going to get bigger, faster and faster and faster, and it's going to approach 0. So again, our limit is 1. Therefore, h of x equals e to the negative x is a left end behavior for model for f of x. Now, I already put in y1, y2, and y3. The function we're dealing with, the supposed right end behavior, and then the left end behavior. Now, the right end behavior is going to draw a line with a little circle at the end, so you'll be able to see it happen. Then the left end behavior is going to be bold, so you'll see that as well. And then here's the window. So let's hit graph and see. Here's the original function. Now coming up will be the right end behavior, and you can see the right end behavior is drawing right along and behaving exactly like the right side of this graph as x approaches infinity. Now the left end behavior is coming down, and it behaved just like the left side of that function. The now try problem number 45 asks us to A, find a simple basic function as a right end behavior model, and B, a simple basic function as a left end behavior model. So in A, finding a simple right end behavior. Well, right end is the limit as x approaches infinity. So if I just think about the limit of e to the x minus 2x and what happens to that, I know its limit is infinity, but more importantly, which part is the significant part of e to the x minus 2x as you go towards infinity? Is it going to be just 2 times that number, really, really large number? Or is it going to be e that has that really, really large exponent? It's definitely going to be e to the x. So my right end behavior is going to model e to the x, the significant part as x approaches infinity. So now we're going to test the limit as x approaches infinity of our function e to the x minus 2x over e to the x. Again, break apart the numerator over the denominator. And the limit as x approaches infinity of e to the x over e to the x is going to be 1. The limit as x approaches infinity of 2x over e to the x is definitely going to be 0. E to the x is going to get bigger much faster, so you're dividing by this larger and larger number. So therefore, since the limit as x approaches infinity of our function divided by e to the x is a right end behavior model. Now the left end behavior model. Well, let's talk about the limit as x approaches negative infinity of our function, e to the x minus 2x. Now I know that that's going to be negative infinity, but which one is the more significant part? Well, if I start plugging in negative numbers, more and more negative numbers, e to the negative x, or e to the negative infinity is going to approach 0, because that's going to drop down to the denominator and it'll be 1 over this really, really, really large number approaching 0. So the significant part in this one is negative 2x. So I found the limit as x approaches negative infinity of our function divided by our left end behavior model, split up the denominator, and looking at the limit as x approaches negative infinity of e to the x over negative 2x, e to the x, as you plug in negative values, is going to drop this down into the denominator, again having a limit of 0. Now on this side, 2x over negative 2x simplifies to be negative 1. So if I'm subtracting a negative 1, my limit is positive 1, and therefore y equals negative 2x is a left end behavior model.